Okay, hello everyone. This video I'm going to show you the example for mechanical energy conservation. Okay, we will use the mechanical energy conservation to analyze some problem. Okay, this is an example from our textbook. Okay, so the problem states the problem description is that is actor here. Okay, actor here, and he want to do some performance. So he want to swing from its initial position I here and to the final position. He want to swing from the I to F. Okay, and during this performance, he doesn't want the sandbag lift up. Okay, yeah, I think in the class I say the actor want to lift the sandbag when when he swing from I to F, and when he swing from I to F, at F he want to lift the sandbag up. Okay, that's what I say in the class. Okay, but when I look back this problem in detail, he said he doesn't want the actor doesn't want the sandbag lift, and when he swing from I to F. Okay, it's kind of reverse concept. Okay, but actually the calculation process is the same. Okay, you can even if I misunderstood the problem a little bit, but the calculation procedure is the same. Okay, so so back to this problem. So the actor doesn't want the sandbag lift up when he swing from I to F. Okay, and he want us to calculate that what's the maximum angle theta for the actor to complete this process. Okay, so actually this is a energy conservation problem, or specifically mechanical energy conservation problem, and is also combine a little Newton's second law of motion. Okay, so the problem is kind of quite complicated. Okay, so and first of all, let's first do a little force analysis, and then we can get more understanding of this problem. Okay, so let's go back to okay, let's first starting the point F at point F. At point F. Let's first do analysis. Okay, at point F. Where's my pen? Okay, at point F. At point F. Okay, let's focus on the point F. That's final position at that particular point. Okay, let's draw a free body diagram of the at point F. So let's start from the simple one. Okay, the sandbag. Okay, at the point F. Okay, at the point F, the sandbag is here. Okay. Okay, so this sandbag connect to this actor with a rope. So he will feel a tension, right? If a tension, he will feel a tension. Okay. Okay, and also it will also have the tension. Okay. And also yeah, feel the gravity. Gravity here. Yeah, the gravity. Not gravity. Yeah, it's weight. Weight. Let's call it bag. Okay, that's bag. Okay, that's at point F. The same bag has a tension and has its weight. Okay, that's for the same bag. It's much easier one. Okay, so and at the point F, let's do the analysis on the actors. Okay, at the point F, the actors here. Let's call this actor. Okay, the actor has this fill point because it's lifted in air, so it has the weight. Okay, and you also feel a tension. You also feel tension. Okay, if you also feel tension, you also feel tension. And most importantly, okay, maybe I should write actor here. Or actors, actor. Let's see, spec actor. So at point F, the actors feel the tension and his weight. And maybe the most important thing, when he swing at this point, actually this swing motion is a non-uniform circular motion. It's a non-uniform circular motion. And at this particular point at F, this actor has the centripetal acceleration. Okay, actually, I told yeah. Okay, I'd rather say okay. He's doing a non-uniform circular motion. So in the non-uniform circular motion, we say non-uniform circular motion. You have two components. You have the okay. Let me non-uniform circular motion. You have acceleration. You have tangential acceleration and plus centripetal acceleration, right? At this particular point, at the point F, the tangential acceleration is just zero. Okay, I think I will use another short video to demonstrate this. Okay, and at this point we only have so at the point F we only have acceleration, and acceleration is equal to centripetal acceleration. And how to calculate centripetal acceleration? Okay, the centripetal acceleration rule. Remember that. Okay, centripetal acceleration. Okay, let me write. Let me see. Okay, let's write. Okay, the actor feel the centripetal acceleration and it's point up. Okay, and the magnitude of centripetal motion is. Oh, I'm sorry. Centripetal acceleration is r and v square. Okay, and right now our r is the length of the rope here, so it's capital R, and the velocity at the point F is vf. Okay, vf square. Okay, so okay, that's the information of the bag in the actor at the point F. Okay, so okay, so the problem say at the point F, he doesn't want the he doesn't want he doesn't want the sandbag to do any motion, so he doesn't want to put the sandbag up even at the point F. So and he want us find the what's that? It's a minimum the maximum value. Okay, okay. So at the maximum value, okay, okay. So let's see. Okay, let's do the force analysis. Force analysis. At this particular moment, the tension is equal to W back. Okay, and then analysis. Okay, so let's do the force analysis again for the person, for the actors. So the T is up point up, so it's T minus W actor equal to M actor times centripetal acceleration. Okay, times the centripetal acceleration. And we will have T minus W actor equal to M actor times R BF square. Okay. Okay. So, mm, okay. So let's me. Then okay. So we will find this relationship. We find the tension. The tension has a relationship to the velocity f. Right? So the speed at this point, the speed at F point is related to the tension, tension related to the tension, and tension is also related to your tension. Also was related to your the weight of your bag. Okay, so the velocity F is have the influence to has a connection to your bag. Okay, the weight of your bag. Okay, okay, that's why the velocity at the at point F is very critical to decide whether you can pull this sandbag up or down. Okay, um because you if you have a large velocity, this relationship tell you if you have the large velocity at point F, if you have high velocity at point F, you will have a large tension at point F. If you have a large tension at point F, that means you have a large tension to pull the tension to the sandbag. Okay. Okay. So the velocity will determine whether you can pull the sandbag up or not. Okay, pull this up or not. Okay, so the velocity at point this point F is very important. Okay, and where it is this so the, and this the velocity also relate to your initial position. Okay, why? And the velocity also VF is associated to have a connection between your initial position, your initial height. Okay, why? Okay, so this come back to the energy conservation problem. Okay, because this actor he swing from point I to point F, swing from point I to point F. Okay, and actually there is a potential energy difference, especially gravitational potential energy difference. Okay, here is not very clear. Okay, let me draw more precisely. Let me draw precisely. Okay, suppose the rope R here, the section, the rope section here, the length in this section doesn't change when this actor swing from I to F. So, okay, actually there will be a height change. It's not very clear. So let me draw it for you. Which color is that? Okay, green color. Okay. And this point I, and this is F here. Okay, actually you will see after the clear observation, there is a height difference here. There is a height difference here. Okay, so in the initial position is much higher. So when you swing from I to F, there will be a loss on gravitational potential energy, and the lost gravitational potential energy will transfer to the kinetic energy at F. Okay, initially it doesn't have any kinetic energy. Right? Initially it is at rest. Just went from higher position to lower position, and the gravitational potential energy transfer to kinetic energy. And you have kinetic energy. That means you have carrier velocity. Okay, so for the concept for the energy conservation, the velocity is related to your initial height. Okay, and the initial height, and we will later see you have the initial height as the height difference. The height difference is associated to your theta, to associate to your theta. Okay, okay, I should say height difference. Okay, yeah, that's more precisely height difference. Okay, relate to your height difference and height difference associated to your theta. Okay, we will get here. Okay, so and in this problem, I say use the energy conservation problem. Okay, use the conservation problem. Energy space and mechanical energy conservation problem. Okay, and the mechanical energy conservation problem. Do you still remember that? Okay, the formula. Because this system, we just ignore in this problem, we ignore friction and no external work done on the system. So it's mechanical energy conservation. Mechanical energy conservation. In mechanical energy conservation, what's the formula? Delta K plus delta U is equal to 0. And more specifically, is the kinetic energy difference between the final state and initial state, and the potential energy difference between the final state and initial state. Okay, so for this mechanical energy problem, let's list our information for initial state and final state. Okay, for such problem, we need to list the initial state and final state information. Okay, so that's initial state and final state. Okay, initial state and final state. Okay, the initial state is here. Okay, initial state is here, the starting point. Okay, and at this starting point, I say yeah, initially this actor is at rest. Okay, okay, so at rest, no velocity, so that means no kinetic energy. Okay, no kinetic energy. And what is potential energy? In this problem, we don't have the spring, but we have the gravitational potential energy in this system. So to calculate the gravitational potential energy, okay, let us set this here as the ground zero, the origin of the zero here. Here, let's say it's zero. Let's say it's zero position. The height or origin of height zero is here. So initial position, initial height is yi. Initial height is yi. Okay, yi. So and the mass is actor for actor n times g n times y I. Okay, and that's the initial state. And what's the final state? The final state, like I said, when it swing from I to F, okay, it carry a velocity Vf here. Okay, so its kinetic energy is 1 over 2 m actor. Sorry, m actors. M actor and times Vf square. And do I know anything about Vf? No, yeah, right now I don't know. Okay, and what's the potential energy at the final state? It's y actor times g times, yeah, y right now is yf. Yeah, because the position is changed. Yeah, it's well now it's yf. Okay, so okay, we can back put this information all into the and mechanical energy conservation. So 1 over 2 m actor Vf squared minus 0 m plus m actor times g times yf minus m actors and times g times yi n equal to 0. So let's do a little arrangement here. So this is don't change. Vf squared and mg, let's say m actor times g, then yf minus yi equal to 0. Okay, and I just say the height difference you can associate to theta. Okay, yeah, here we have the height difference yf minus yi, and we want to associate this to theta. Okay, we want to uh, find the yf and yi, and I think it's associated with the theta. Let us see. Can we find it? Yeah, let's look at the graph. Clear, so clear. Okay, so yi and yf. Okay, so the difference is here, and here is let's say yi minus yf. So okay, let's see. Okay, let's see. Okay, so the length of rope during this section doesn't change from position I to position F. So this will, okay, maybe I use the rope. I don't know, ruler. So here is, so let's just see. So assume, okay, here we say, here is also R. Here is also R. Okay, and we want a difference here. YF. Okay, this is the YI minus F. Okay, what is YI minus YF? Okay, YI minus YF. Okay, if you think this, if you look at this clear, more detail, you will have this information. And here is Y cosine theta. Yeah, here. Yeah, wow, so difficult to draw here. Ah, maybe here. Yeah, definitely here. Here. Here is R cosine theta. Yeah, it's here. This section is R cosine theta, and this section is R. So yi minus yf is actually is R minus R cosine theta. Okay, it's yi minus yf. Okay, but now what we need the yf minus yi, right? Yf minus yi. Yeah, yi minus yf is R minus R cosine yr minus R cosine theta. So right now we want a yf minus yi. So it's R cosine theta minus R. Okay, be careful. It's it's R cosine theta minus R. Okay, so we can associate the y difference to associate to theta. Yeah. Okay. Okay. So I think it's almost done. Okay. So we will finally reach this equation. Okay, 1 over 2 m actor vf square plus m actor times g times r cosine theta minus 1 equal to 0. Okay, this equation we got right now using the mechanical energy conservation. Okay, and so next step, what are we trying to do? Okay, okay, we want to find out the G. Okay, we want to find out the T because T is the information we really want because T can determine whether we can pull the sand back up or not. Okay, and also previously we know T has a relationship between the VF square. So actually, so I have to write down. Okay, let me write down the information here. T equal to m factor R squared plus W factor m factor G. Okay, so let's see. G equal to W actors plus M actor times R VF squared. Is that right? Is that right? V squared. Okay. And W actors. And W actor actually is M actor times G. M actor times G plus M actor times R VF VF square VF square R VF square. Okay. Okay, so this is the we get the T tension. Okay, tension has a relationship here. Okay, and so okay, and also we want because we want a T minus or equal to the weight of sandbag. Okay, so let us just consider the equal situation. Okay, because we want the maximum angle theta for not lifting the sandbag. So we consider the equal situation. So we will find this. Okay, because we have a t has the relation with this. So t m actor times G plus M vector times R function V square. And okay, for precisely, let me just write this. And send back. But actually, we only consider this situation now because the maxima is this situation. Okay, so so it's M send back, M back times G. Okay, and the final problem is okay. We should replace something. We should replace something because the in in this equation, G is known. Okay, of course G is known. Okay, R is known. M actor is known. Okay, the only we don't know is VF square. So we have to substitute the VF square to the and replace by the information we have known. Okay, so yeah, I should say it's the final equation we want to use. Okay, I call it one. I call it two. Okay, so the VF. Well, how do we replace VF? We use information of one. Okay, use one to substitute VF square. Okay. Okay, because in question one, the VF can be expressed by meso actor, rope, and the theta. Yeah, and the theta is the one we are looking after. So that's why we want to replace the VF square. Okay, but if you just substitute the VF square directly, that would be kind of too complicated. So we just let me see. Okay, from one we want to make because I want to make a substitution much easier. So okay, let me start. Okay, from one we can do a little trick. Okay, I divided by one by. Okay, I divided the one total by R. Okay, and then I will have the 1 over 2 M actor and R VF square plus M actor times G times cosine theta minus 1 equal to 0. And then I times 1 over R and times 2 times 2. And we will have M actor RVF square and plus 2M actor times G and times cosine theta minus 1 equal to 0. Okay, and so why we want to do this? Why do I want to why do I do this? Okay, because I want to get this relationship, and then I will have a relationship that the M actor times R BF squared, so equal because it moving into the right hand side, you have minus sign, so it will become like this: 2 and 3 times 1 cosine theta. Okay, and here from this here. Okay, here I need the more common here. Why the more common from two we will have this equation from 2. So this is 3. Okay, this is 3 from 2 and 3. 2 and 3 from 2 and 3. We'll have this equation. This is 4 and back. This is BAG. Okay, so I can substitute. So I get this purple. Oh, not purple. I get this equation right now. So I can replace this term. Okay, did you see that? I can replace this term in 4. Okay, I can replace all this term in 4. Yeah, you see that? I can put this term in 4. Okay, I can put this term in 4. So, so I should say I call this is mm, 5. So in the from 4 and the 5, okay, what we will have the M actor G M actor times G and plus 2M actor times G times E minus cosine theta square root M back times G. Okay, so okay, that's the final answer. The final answer is here. Okay, where should put this? Here. Final answer. Okay, so first of all, for this final equation, okay, G can be cancelled out, divided. Okay, so and the other is okay, the mass of actor is what 65, and sandbag 130. Or okay, and length of rope 3 meter. So there's nothing to do with the rope. Nothing to do with the length of rope, really. Yeah. Yeah, it's really nothing to do with the length of rope. Yeah, very strange. Okay, M actor is 65. M actor is 65 kilogram, and bag is 130. So that means M bag is double than the M actor. So if we divided the M actor, so we divided the M actor, so this will become 2. So the final equation is, okay, let's see if the result is right. It's 1 plus 2 minus e cosine theta 2. So it's root 2, 1 minus cosine theta. Okay, and then 1 minus cosine theta number 2. So cosine theta, 1 over 2. So it's really cool. So the theta is 60 degree. Okay, theta should, yeah, theta should less than 60. Yeah, less than 60 degree. Should less than 60 degree. Okay, and right now we want to find a maximum value of the theta. So it's we consider this situation. So this theta is equal to 60 degree. I think that's the final answer. Okay, so this energy conservation associate problem, yeah, it's kind of pretty challenging because it's include the Newton's second law of motion, and especially the centripetal acceleration. So that's more this problem. Kind of very complicated. Actually, yeah, it is complicated. Yeah, and this is an example problem I referenced from the survey 10th edition. And the mechanical energy conservation problem in our textbooks is kind of too easy. So that's why I want to use the example to demonstrate energy conservation calculation. Okay, so let's just combine what we have done now. Okay, Newton's law of motion and energy conservation, and put this all together. And I think I will make a little video so to show you why at this point F there is only a centripetal acceleration and no tangential acceleration. I will make a small video for that. Okay, so a small short video for that. Okay, so here's the problem. Okay, hopefully you can get more understanding of this problem. Yeah, the calculation procedure is also not quite easy. Mm. Okay, so here's this example, and I'll start video here. See you in another video. Okay, bye bye. Yeah, maybe I should make this more clear here. Okay, it's 1:30. Okay, okay. So see you. Bye bye. Very complicated problem.